Welcome to First Principles Daily, episode 32 for July 7th, 2026. Today we reason from raw materials, not analogy. Burning fuel for heat hits a hard 100% efficiency wall, yet heat pumps routinely deliver 3 to 4 times more heat than the electricity they consume by moving heat instead of creating it. A typical home heating bill today reflects the cost of generating heat from scratch, whether through gas combustion or electric resistance. That bill captures every step of turning fuel or current into new thermal energy inside the house, even when the surrounding air or soil already holds far more warmth than the building needs. The raw physics of the situation shows that most of that heat already exists in the outside air or ground, and the real expense is only the modest work required to concentrate and move it indoors. Once we accept that the thermal energy is already present outside, the engineering task narrows to the compressor work that gathers and relocates it rather than the much larger task of creating the energy in the first place. Heat pump systems that perform this concentration routinely achieve coefficients of performance between 3 and 4, meaning they deliver 3 to 4 units of heat for every unit of electricity supplied. A coefficient of 3, for example, means that for every kilowatt hour drawn from the grid, the machine returns roughly 3 kilowatt hours of heat to the living space, while a coefficient of 4 raises that return still higher. The gap between that performance and the price of a finished installation is where the first principles opportunity sits. Heating systems in most buildings still follow the long-established pattern of burning fuel on site or running resistance coils. That pattern grew out of the ready availability of coal, oil, and natural gas, plus the simplicity of piping or wiring a combustion device into an existing structure. Over decades, every trade, every code book, and every financing worksheet aligned itself with the assumption that heat would be made on the premises rather than moved from outdoors. Installers, code officials, and financing models all became organized around combustion appliances, so the default path for any new or replacement system remains a furnace or boiler. The finished cost of a typical residential gas furnace plus ductwork runs on the order of several $1,000s, while a comparable heat pump installation often lands higher because it requires both an outdoor unit and indoor air handling changes. Those higher upfront numbers feel normal inside the industry, because each project is still treated as a one-off job involving site visits, custom refrigerant lines, electrical upgrades, and separate trades for sheet metal, controls, and commissioning. Fragmented supply chains add carrying costs. The compressor may come from one supplier, the coils from another, the controls from a third, and the refrigerant from a fourth, with markups applied at every handoff. Each handoff adds margin and delay, so the final invoice reflects not only the parts themselves, but the cumulative carrying costs of keeping separate inventories aligned across many small projects. Permitting and inspection timelines stretch the project duration, during which labor and equipment sit idle. Cold climate performance concerns, although largely addressed by variable speed compressors and improved refrigerants in the last decade, still trigger conservative sizing rules that increase equipment capacity and therefore price. One objection sometimes raised is that older homes lack sufficient electrical service. In practice, this adds a panel upgrade step whose cost is real but finite and amortized over decades of lower operating expense. The upgrade itself is a one-time outlay measured in a few $1,000s at most, yet the operating savings compound every winter because the same kilowatt hours now move 3 or 4 times as much heat as resistance heating would have produced. Another objection is that combustion equipment feels simpler because the fuel itself carries the energy. Yet that simplicity hides the ongoing fuel delivery logistics and flue maintenance that heat pumps avoid entirely. The delivered cost of heat remains anchored to the combustion baseline even though the underlying physics no longer requires it. If a magic wand could instantly arrange the necessary atoms into a finished heat pump system, the dominant expense would not be fuel, but the small quantity of electricity needed to run a compressor across a temperature difference, plus the materials inside the machine itself. A rough accounting starts with the major commodities, several kilograms of copper for the heat exchange coils and windings, aluminum or steel for the cabinet and fins, a modest amount of refrigerant, and the electric motor and electronics. Commodity prices for those materials fluctuate, yet their combined value in a typical residential unit is on the order of a few $100s at most. Adding the electricity required to move heat across a 30 to 50 degree temperature gap for an entire heating season yields another few $100s in energy cost, depending on local rates and climate. That sum is the approximate magic wand floor. Current installed prices for the same capability sit several times higher, producing an idiot index that is still in the double-digit range once the material and energy floor is used as the denominator. To see the ratio clearly, divide the finished installed price by that few $100 floor. The result lands well above 10 because the materials and seasonal electricity together form the denominator. The largest share of that gap appears in the on-site assembly steps, running new electrical circuits, modifying or replacing ductwork, pressure testing and charging the refrigerant loop, and coordinating multiple subcontractors. Each of those steps carries labor rates, travel time, and risk markups that compound because the work cannot be parallelized or standardized across thousands of identical units. Another slice comes from the regulatory and permitting layer, where each jurisdiction's inspection sequence adds days or weeks without changing the physical product. Manufacturer margins and distribution layers sit on top, reflecting the low production volumes that still characterize the North American market relative to combustion equipment. An objection sometimes heard is that houses differ so much that standardization is impossible. Yet the variation is largely in the final connections, not the core vapor compression cycle itself. Because these costs are accepted as normal, the finished price remains far above the physical minimum, even though the thermodynamic advantage is already proven in the field. A redesign effort would begin by treating the entire heating service as a manufactured product rather than a field-assembled collection of parts. Factory-built, pre-charged modules that require only electrical and airside connections could eliminate most refrigerant handling labor and leak test time on site. Standardizing a small number of capacity sizes and connection interfaces would allow higher volume production of the core compressor coil assembly, driving the material and assembly costs closer to the commodity floor. Next would come simplification of the electrical and controls package so that a single qualified electrician can complete the connection in hours rather than days. Policy changes that credit measured seasonal performance instead of nameplate combustion efficiency would shift incentives toward the higher performing machines. The genuinely hard constraints are real. Refrigerant safety standards limit which fluids can be used at scale. Cold climate capacity still requires larger heat exchangers or supplemental heat at the extreme tail of the temperature distribution, and the existing housing stock contains widely varying duct and electrical infrastructure that resists complete standardization. Even so, each of those constraints can be attacked with targeted engineering rather than accepted as permanent cost drivers. One concrete first move is to qualify a single, low global warming potential refrigerant across multiple climates so that inventory complexity drops. A second move is to certify prefabricated mounting frames that fit common foundation and roof penetrations, cutting layout time. A third move is to bundle the outdoor unit with a matching indoor coil that shares the same mounting footprint, reducing the number of field measurements. The prize is a delivered cost of heat that approaches the electricity plus materials floor instead of remaining tethered to the combustion paradigm. When the dominant expense in delivering heat is the sequence of site trades and regulatory steps rather than the copper, steel, and electricity inside the machine, the signal is that the process itself has become the bottleneck. When an alternative method already exceeds the theoretical efficiency limit of the incumbent technology, the remaining task is to remove the layers that were built around the older physical constraint. Tomorrow's episode will take up another concrete case or another domain where the same gap between floor and finished cost is visible. The first clear signal that someone is closing this particular gap will be a heat pump product line whose installed price in volume markets falls to within a small multiple of its commodity material and seasonal electricity content. That's First Principles Daily for today. If this changed how you see what things cost, share it with someone who'd appreciate it and subscribe wherever you listen. I'm Patrick in Vancouver. One example or one opportunity every day. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.